Hi everyone, my name is Yueyang Pan. In this talk, Ruihan Li and I will introduce our work titled The First 5G LTE Comparative Study in Extreme Mobility. We are both undergraduate students and contributed equally to this work. We are instructed by Professor Chen Renxu, and the work is entirely done by Peking University. We are standing on the eve of 5G era. The deployment of 5G is speeding up worldwide and is across more than 112 countries at the end of 2021. Moreover, IMT 2020 requires 5G networks to achieve multi-gigabits per second throughput and sub-millisecond latency. There are significant improvements over the state-of-the-art LTE technology. It innovates new applications such as Ultra HD video streaming, highly interactive VR games, and so on and so forth. Meanwhile, high-speed rails, or HSR, are becoming popular. China has built the world's largest and most extensively used HSR network. It has a total length of over 40,000 kilometers and transports billions of passengers every year. The benefits of HSR have also been advocated by both the States and the European. Given the construction of HSR is speeding up worldwide, it is important to provide seamless network experience on board. Though 5G claims to support mobility up to 500 kilometers per hour, its real performance on the extreme mobility remains a mystery. In this work, we fill the blankness by answering several questions. First, does operational 5G on HSR fulfills its throughput and latency goal as promised by IMT 2020? Second, how does 5G's performance suffer from high mobility, especially facing frequent handovers and large signal variances? Third, to what extent can applications such as web surfing and video streaming leverage 5G for better services? We first introduce some background knowledge. 5G has two deployment modes, non-standalone or NSA and standalone or SA. 5G NSA reuses LTE's control plane and the core network EPC. It's designed for fast deployment. Instead, 5G SA has its own core network 5GC. As a considerable part of countries are transitioning from NSA to SA, the performance of both matters in the near future. To investigate previous questions, we designed several types of experiments focusing on throughput, latency, and applications. During experiments, we collect baseband logs, IP packets, and application logs to analyze the network performance in a cross-layer manner. As shown in the figure, we run these experiments in parallel using three separate physical resources. The cloud server is deployed with enough ingress and egress bandwidth. We travel back and forth to evaluate different radio access technologies and deployment modes. We conduct our experiments on the Beijing to Zhangjiakou intercity railway. It's the only line with a maximum speed of 350 kilometers per hour and full coverage of LTE, 5G SA, and NSA at that time. We in total cost 1,789 gigabytes mobile data and traveled more than 16,000 kilometers for all our three clients. In the rest of the talk, leveraging our unique data set, we will detailedly compare the performance of operational 5G and LTE on extreme mobility. We start from considering whether operational 5G on HSR fulfills its throughput goal. The figure first shows the average TCP throughput in LTE for three clients. 5G SA improves the throughput of TCP from 20 Mbps to 223 Mbps, which is an 11 times boost. Mid-band 5G cannot achieve multi-gigabits per second bandwidth because of limited wireless channel resources. 5G NSA, however, does not perform as well as 5G SA because of fallback to LTE handovers. QUIC also performs worse than TCP. We attribute the reasons to ISP QoS for its higher loss rate and to BBR variants for its less aggressive implementation. Even QUIC, the protocol with many years' effort on standardization, does not fully utilize ultra-high bandwidth in 5G. Thus, we highlight the importance of end-to-end evolution. Next, we consider how throughput is affected by signal conditions. We begin from some statistics. The signal conditions are described by two metrics, RSRP and SNR. The two figures show their average in each month. We can see the signal conditions are stable for LTE and also for 5G. It suggests our experiments are not interfered by irrelevant factors such as infrastructure upgrades. We also note that both RSRP and SNR statistics show 5G works at obviously worse signal conditions than LTE. So how does the signal variance influence the throughput? To answer the question, we first divide RSRP and SNR into 5 categories: poor, fair, average, good, and excellent. We show the normalized throughput for each SNR and RSRP category. The figure shows that 5G has more robust throughput to signal variance than LTE. We examine the trace and find that LTE base stations allocate less physical resources when the signal condition is poor. It makes the throughput in LTE even worse. Then we consider how throughput is affected by frequent handovers on HSR. We propose the first taxonomy for for 5G NSA and SA handovers. The taxonomy is based on the handover signaling process. It helps us to capture handover events from the baseband logs and analyze the performance implications. The difference between NSA and SA is that SA only synchronizes with the 5G stations, while NSA may synchronize with both LTE and 5G stations, and both may fail during the handovers. We first show the process and taxonomy for SA. We use type 1 to denote successful handovers. For failed handovers, 5G SA and LTE handovers behave similarly. Both type 2 means synchronization failure, but the radio link is recovered later. Both type 3 means the packet buffered in the base stations are lost, and other user information is lost as well. NSA is another story. We use type 2 to denote the failed LTE handovers, which implies the 5G connection is released. It will go through the similar process as LTE only mode. When 5G handover fails, there are 4 cases depending on whether the 5G connection releases and whether an extra LTE handover is triggered, as shown in the figure. For example, both type 5 and 6 introduce additional LTE handovers. We demonstrate some handover properties first. The first figure plots the CDF of handover intervals for LTE, 5G NSA, and 5G SA. An interesting observation is the step-like curve of 5G SA. Step 1 is caused by signal variance, and handovers occur between base stations back and forth. Near step 2, 5G SA's handover interval is longer than that of LTE. It's because 5G can work at low signal strength and tolerate worse signal conditions than LTE. The second figure plots the CDF of the handover durations. We draw 2 important observations. The first one is that successful handovers suffer from longer processing delay in 5G, which prolongs the duration. The second one is that the context loss handovers have shorter durations in 5G because of the introduction of new fast connection mechanism. We next analyze the impact of handover on throughput. These figures show how average throughput changes near handovers. We focus on successful handovers. On the one hand, before handovers, both 5G, NSA, and SA suffered from less throughput drop than LTE. As the signal conditions are getting worse, it verifies the better robustness of throughput in 5G. However, the throughput in the first second after the handover drops more in 5G. We attribute it to the insufficient buffer size at the base station, which is unlikely to scale up as the bandwidth. Now we see handovers in 5G may have longer duration and may cause severe throughput drop, which show that there are still deficiencies to be addressed on the road to maturity of 5G.
Hi, I'm Ray Hanley. Now let's turn our attention to the latency of operational 5G on HSR. We begin with the round trip time of 4-speed TCP streams. We can learn from the graphs that 5G has shorter and more stable RTT. But why? To find out the reason, we design separate experiments to break down the end-to-end RTT. The client sends the packet to the server and the server echoes them immediately. The sending rate is low enough to avoid any queuing delay. The end-to-end RTT is the RTT measured by the client. Inside the end-to-end RTT, the baseband processing delay is caused by radio processing in the baseband. And waiting for uplink resource allocation further lead to uplink waiting delay. The two delays compose the protocol delay. Also, a large packet can be divided due to limited physical resource, causing segmentation delay. Packet retransmission may lead to actual retransmission delay. All the four delays together compose the radio access network latency, or the RAN latency. The backend latency is the end-to-end RTT minus the RAN latency. It can be seen as the RTT measured by the base station. The snapshot visualizes the backend latency and the end-to-end RTT. We notice that backend RTT is stable except for the change across handovers. Instead, the RAN latency occupies a considerable part and contributes to almost all fluctuations of end-to-end RTT. The LT snapshot is similar, but the RAN latency is larger and more variable. Then we demonstrate the details of latency breakdown. The first table shows the results of 5G. The average RAN latency is around 60 milliseconds. Within it, segmentation delay accounts for a large part. It means base stations won't allocate enough resources in time. Protocol delay notably accounts for more than half of the RAN latency. The second table presents the result of LTE. In comparison, each component is longer and also more variable. The reduced protocol delay shows 5G optimizations, such as the pre-allocated uplink resource. However, original 5G is still far away from the sub-millisecond latency goal. Thus, the gap between the standard and the reality needs more attention. To step forward, renovation is necessary at both client and base station side. Next, we will study how frequent handovers and signal variance affect latency. We show relationship between the end-to-end RTT and ISRP SNR handovers in the three figures. We found that these factors influence LTE's end-to-end RTT heavily, but 5G's mildly. Thus, we conclude 5G's better robustness to signal variance holds not only for throughput, but also for latency. Finally, we are going to investigate two applications on HSR, web surfing and video streaming. In web surfing, three figures show the average page loading time for most popular websites. We notice that 5G decreases page loading time regardless of page size. However, 5G SA prolongs some DNS lookup time, which suggests the immaturity of 5G core network. It is another deficiency on the road to the maturity of 5G. And video streaming is believed to benefit from 5G's ultra-high bandwidth, particularly under extreme mobility. Our experiments cover several deployment-ready or state-of-the-art adaptive bitrate algorithms, The three figures show the stop cent and the average bit rate of them in LTE, 5G NSA, and 5G SA. Unfortunately, none of them behave better at both average bit rate and stop cent, which calls for HSR and 5G specific ABR algorithms. So, in a word, we conducted the first 5G-LTE comparative study in green mobility, the first taxonomy of handovers for 5G, and the first latency breakdown of both LTE and 5G. We highlight the importance of end-to-end evaluation, the large gap between the standard and the reality, as well as several deficiencies on the road to the maturity of 5G. Okay, that's all. Thank you for your listening.